Alright, hey guys, what's going on? So today we are going to be talking about curvature as a force, okay? In this video, we're going to see some very interesting connections between curvature and physics, and then in the next video, we're going to talk about curvature of curves and exactly what curvature means when we're talking about, say, geodesics or curves in 3 space as opposed to surfaces or anything like or something like that. But we're starting to sort of look at curves themselves, not surfaces. So we're deviating away from talking about spheres, hyperspheres, and all this kind of stuff, and we're going to be looking at curves themselves. Enough about the intro. Make sure to hit that like and subscribe button if this is the kind of content you really like, and make sure to go onto my Patreon page as well. With that being said, let's get straight into the content. Alright, so we're talking about the curvature as a force today. So in the last video we talked about curvature as the double derivative of a parametrized path. Okay, now we're going to be investigating the curvature in more physical terms. And we're going to summarize a bunch of things later as well. So if a particle of unit mass, this is sort of Newton's hypothesis, if you will. One of Newton's hypotheses. He was a very prolific figure, not just in mathematics, but also in physics. But he posited that if a particle of unit mass is launched at unit speed, the curvature of its path is the force that the particle experiences given by the curvature of that path. So his hypothesis essentially is that curvature equals force. Okay, so when a particle moves along a path, that moving along a path, if there's curvature in that path, that curvature gets translated into a force that particle feels. Okay, because if there was no force, it wouldn't curve in a different direction. That was the thought process, in very simple terms. But anyways, let's now investigate this and see how this plays out. So we have this arc length formula. We're going to take a look at this picture here. My drawings aren't great. This isn't a perfect circle, but this is intended to be a circle. And the circle here is, this is a radius. The radius is going to be posited to be 1 over the curvature at some point P. And we have two tangent vectors at point P, and one we're going to say at point Q. Okay, and then from P to Q, we can approximate, there's going to be some curvature, which is sort of right here, what I've shown in this mini picture here, but from P to Q, we're going to approximate this distance with this arc length. So the arc length is delta S, and we're going to say that delta S is equivalent to R delta phi. So here's that delta phi. It's the angle that makes the curve, or makes the arc length. Okay, so depending on how big this angle is going to determine the length of that arc. And then also how far away it is from the center, right? So this is a formula for arc length, and so we're positing again that the curvature is going to be equal to 1 over the curvature. This K here is a curvature, so we can replace R with 1 over curvature, and what we get is that the curvature is equal to the change in the angle over the change in the surface area. Okay, so if there is a large change in the angle, and so if this ratio is large, right? So if this ratio is large, then kappa, or the curvature, is going to be large. Okay. And so what does this mean? Well, we can actually kind of replace this really quick. I just want to show R. We could take this formula and say R is equal to delta S over delta phi. Right, and so what this tells us is that if the delta S changes dramatically, or we could say, okay, if R is huge, right, we can imagine R being massive, massive, massive circle. If that was big, then that means that the rate at which this is moving is much faster than the rate at which the angle is moving. So you can imagine a giant circle. Imagine this is a really, really big circle. If there's a tiny, tiny change here, and the circle is huge, then the arc length subtended is going to be really, really big. So you could sort of picture that. Okay? And so that's what this is saying, that the curvature is sort of the inverse of that. Okay? So now we come down to this picture now. We're just taking a look at this triangle now. So this is at delta angle. And here's our tangent. We have a tangent space at Q. We have a tangent space at P. And the change in the tangent vector, the change in T, okay, which is going to be this vector here, is going to be equal to the angle, delta angle, times some normal vector, okay? And we're going to see exactly what this normal vector is going to be later. But what we can therefore say is that the normal vector, right, so if we divide everything by delta S, right, so delta S is the arc length, okay? Divide both sides by delta S, we get this formula. And we know that this here, what we said was right here, okay? So the change in the tangent vector at P with respect to the surface, the arc length, right? So the change in the tangent vector with respect to the arc length is going to be the curvature times some normal vector. So the curvature tells us how the tangent vector changes as the arc length changes on the curve, right? So, and we'll see more about what this n is later. But anyways, we now invoke some physics, okay? We're going to say that the velocity is going to be proportionate to the tangent vector, right? Because this is sort of intuitive, right? Because tangent vector is the derivative of some position, right? So, and velocity is the derivative of some position. And so we're going to say that the velocity is a some scale version of the tangent vector. So however you scale the tangent vector in this picture, it can be squeezed or it can be stretched. That's going to represent the velocity of some particle at point P. Okay? And then delta S, that's the arc length, is some scale length of how long the particle, it's some scale length of time, right? So we're parameterizing the curve, and the arc length is going to be some scale version of some change in time. Okay? All right. So now let's go up here. And now that we have invoked those two equivalences, we've evoked time and velocity. These are physical entities, and we're relating them to mathematical entities. We can now write a change in velocity is a change in the tangent vector, right? So this is really just from here. We just divide both sides by v and we take the change in both sides, right? So the change in both sides divide by v. Therefore, we could say that dt ds is equal to this, okay? Because dt we found was this, and ds we found was this. So we have this. And so v squared times t ds, or dt ds, is equal to dv dt. Right? This is the dv dt has to change in some position. This is the change in the velocity, right? Not the position. So this is actually an acceleration. Okay? And keep that in mind, right? Because F equals ma, a is an acceleration. If a is an acceleration, then force, we're going to see exactly how force gets invoked here, just as we've sort of alluded to in this statement here. But anyways, now, so dt ds we found was this, because if you remember from right here, okay? So Newton's equation becomes If F equals ma, this is something you learn in physics, F equals ma. Well, this is A, right? So if this is A, then this is A, okay? This over here, if this over here is A, we could say M, and this is all A. Okay? But so what we've done here is we've said that the force is therefore proportionate to some scale factor, mass times the curvature times some scale factor times the normal to the tangent vector. Okay? And that's exactly what we've sort of alluded to right here. If a particle of unit mass is launched at some unit speed, the curvature of its path is the force F that the particle experiences. Okay? And the curvature given by the curvature of the path. So the curvature is sort of defined by the normal vector with respect to the tangent, right? So you have some curve, and we have the tangent curve, and so the normal vector is going to tell us in which direction this the particle is. So this is the particle. It's feeling some inward force, and so it's going to travel like this, right? So it's going to travel like this as it's feeling that force. And then at this point here, it looks like the force is now going to be in this direction because this is concave, and it's going to travel this way. So forces are pushing on this particle at every point along this curve, causing it to causing the particle to move in a certain direction, right? So we can imagine these are all normal. These are all normal to tangent vectors, and these normal vectors are telling us something about the force that the particle experiences. So up to this point, we've been dealing with paths that can be expressed as a graph of a function. But what if we can't do this? Okay, so the idea here now is we have this particle at point P. We've determined that it experiences a force, and that force is given by the normal vector. And what we've also determined is that we can parameterize the curve, this curve here, by some function. My apologies for the dog barking. By some function. But what if we can't do that? What if we can really only describe the position of the particle? Well, if we can only really describe the position of the particle, we can do it in terms of x and y, right? And so if this is the tangent vector, this tangent vector tells us something about the velocity. So this is going to be the velocity of the particle on some x-axis, and the velocity of the particle on some y-axis, and they're both going to construct the velocity of the vector at some point. So now that we have this picture in mind, let's so the curve is we're going to let the curve be the orbit of a particle whose position is x and y. So its position is x and y. The tangent vector t, it tells us something about the velocity, and so we can break up the velocity into x and y components. And what we're going to do now is we're going to take a look at this picture, which I've copied here, and we're going to prove this right here in a bit. And we're going to see how we can express this curvature in terms of x and y, as opposed to what we did earlier, which was in terms of a parameterized curve f. All right, and so let's do that. So we're going to say v has some x and y components to it. We can say that the tangent of this angle is, again, opposite over adjacent. And so we could take the derivative of this tangent, which is the derivative of sine over cosine, and we get this. Okay? We can simplify a few things to get this, and then we get this guy right here. Okay, so because this is 1, right? That's just a formula in trig, that's 1. All right, so from this figure we find that v squared is this, right? So this squared is equal to this squared plus this squared. All right, so that's this right here. And then we get this guy, and then the cosine is equal to adjacent over hypotenuse, right? So this is all just math, right? So the cosine of this is just the adjacent over the hypotenuse. All right, so that's this. That's the x component over here. So we get x dot over v equals the cosine of this angle. All right, so far so good. This is really just trig, some math involved, some calculus, not stuff too scary. And so given that we said that the arc length was proportionate to the radius, which is the inverse of the curvature, and the angle subtended, and we also said that S was a parameterized version of T, therefore we can say that this here is equal to the curvature times the change in T, and so this as a function of T, or did this divide both sides by T, we get a derivative with respect to time, and then we get this. Sorry, this is a few pauses. I have someone texting me on my iPad, which is a little bit distracting, but getting back to so getting back to this right here, so this is what we calculated up here, okay? We said that that was this, all right? But now we say that this guy is this, right, from right here. So we have that, so we have this relationship. We factor things out now, right? Because we said cosine squared of phi. Well, cosine, we said, was this. So square it, we get this. And so we get this. Okay. A lot of math, a lot of substitution, but we're getting to the point soon. And so we land at this equation, right? This is, I'm not going to circle this actually. I don't, because this is just a step towards an overall aim. Oops. This is just a step to an overall aim that we want to get to. So I'm just going to label this as equation 1. Okay. Let's keep that equation in mind, and now let's recall this equation, or this triangle up here. So the tangent of this angle is y over x. Okay. Well, we could take the derivative of y over x, the two derivatives here, and we get this. All right, so using equation 1, right, that equation, which is here, we get this. Right, okay. So just to be a little bit clear here, here's our x squared. So let's, here, I just want to, so d tangent of theta by dt, right, that is d tangent of theta by dt, so it's this times this, which is where we get this from. So what we get is this. All right, so to summarize our formulas from the last video and this video, we have a coordinate-free now formula for the curvature of any arbitrary curve. Okay, if we parameterize it by some function, this is a coordinate-free formula. This was from the last video. From this video now we found that we have a coordinate formula. And then we also had that the curvature is related to the force, which also, and the force is related to the normal. And this is going to be important for the next video. So in the next video, we're going to talk about 3 important vectors that define the curvature, or 2 different types of curvature actually, of a curve. Okay? So what we found so far is that the tangent is related in some sense to a velocity, right? That's the position, the derivative of some position. The force is related to the normal of that tangent, okay, along some curve. But then we also have this B. If we want to construct an actual coordinate frame here, three-dimensional coordinate frame, we have this B vector also that we can put. Okay, we're going to talk about this in the next video in more depth. But to summarize, T is the tangent, F is the normal, B is what we're going to call the binormal, and this gives, T gives us velocity, N gives us a force. B is going to give us a torsion. Okay, we'll talk about that later also. T and N form a tangent plane, so that's the tangent plane along the curve. And T and B are going to form an osculating plane. I always used to read this as oscillating, which sort of confused me a little bit, but this is going to form an osculating plane that's going to define the curve as well. And last but not least, it's important to keep in mind that because we are dealing with planes, for all practical purposes, we don't need to consider z or z dots, right? Because we are dealing with planes, right? So the plane, again, this is the plane in which we construct our vector or velocity vector, right? So that tangent plane is going to be, I'll do this in a different color. Right here. Right, so we can construct, say, this was that x dot and our y dot. Okay? And so that's the picture we have. This is, so what we're going to do next is we're going to talk about torsion. We're going to talk about these vectors specifically and how they play a role in defining two very fundamental concepts within differential geometry, namely torsion and curvature. So with that being said, make sure to hit that like and subscribe button. If you like this kind of content, make sure to go onto the Patreon page as well, where you can support this channel. I'll see you guys in the next one.